Let's talk about why data science needs math. Here's the objectives slide for this lecture. Please pause and read the objectives before proceeding. So to start, the first thing I want you to know is that this lecture is primarily concerned with level 2 type data science positions. Don't misinterpret this lecture to mean that you need mathematics at this high of a level to do data science in general. If you intend on going into level 1 reporting where you're just doing operational reporting with means and totals, you don't need this level of sophistication. But if you intend on going into anything related to forecasting, predictive modeling, statistical modeling, or AI, you will find that you'll run into this material and the concerns of this lecture eventually. So recall from a few lectures ago that I talked about level 2 data science. There's all this math associated with level 2 work, linear algebra, probability, and statistics at a master's level, which requires at least 3 semesters of calculus. Given the prerequisites of DSI 2000 and how much work this would be beyond DSI 2000, you have every right to be skeptical about this. A completely reasonable question would be, why do I need to do all of this math? That's a question that I aim to answer in this lecture. But before we start talking about math, let's explain why you need this math from an ethical perspective. Here's the thing you should know about machine learning. Most algorithms you find in machine learning textbooks are super easy to code. In Python, it's usually about 4 or 5 lines of code to execute a machine learning algorithm. And guess what? You could easily go online, figure out how to use scikit-learn, and write 4 lines of code to execute a support vector machine, for example. If you wanted to learn machine learning, you could just enroll in a course online, move at your own pace, and learn how to execute code that does machine learning. I'm here to tell you that DSI 2000 is not that type of class, and my recommendation is that if you're really going to do serious machine learning, you need to learn some calculus and linear algebra. Often, students view what I'm saying here as gatekeeping, but there are actually ethical reasons for this. First of all, if you wanted to take the I'm just going to learn the code approach to machine learning, you should know that there's plenty of people that can do that, and it's not going to make you very competitive in today's job market. It's also concerning from an ethical perspective. This is a headline from MIT Technology Review, talking about how it's problematic that there are all these sophisticated algorithms and few people who actually know what these algorithms are doing. Taking all of this into account regarding AI and machine learning, the first thing I want to tell you from my experience as a data professional is that despite all of the hype between AI and machine learning, they're rarely the correct tools to use in practice. Why is this? The best way to describe this is what I call the explainability versus complexity trade-off, which is as follows. More complex models, such as machine learning and deep learning algorithms, have output which is more difficult to explain to non-technical people, so high complexity implies low explainability. And, in addition, simpler models such as regression have output which is easier to explain to non-technical people, so low complexity implies high explainability. This is what the explainability versus complexity trade-off is. Just so you're aware, this trade-off is the motivation behind what is known as explainable AI. How can the output of an AI model be made more explainable to non-technical people? I'm personally skeptical that this movement will take off, but I'm paying attention to it. So you're probably wondering why one should care about explainability. One usually thinks that it's sufficient just to get a prediction out of a model, but in many situations, a prediction alone is not sufficient. Here's one example. Suppose you're hired as an HR analyst, and you're tasked with creating a statistical model to evaluate job performance that could potentially fire employees. In such a situation, the output is usually a score out of 100 for each employee. There are several concerns one is to take into account in this situation. If you use a machine learning algorithm to do this that isn't particularly explainable, you'll just end up with a score out of 100 for each employee, without any output really indicating what factors drive the employee's score. From an ethical perspective, this is extremely concerning. If you, as an employee at a company, were marked as a low performer at a company due to a statistical model, you would probably want to know specifically what drove the model to mark you as a low performer. This is often not possible, particularly with complicated machine learning algorithms. Let's consider the opposite side of a spectrum. Suppose you used a regression. The regression would give you some explainable output about the factors marking you as a low performer, but there's also an additional aspect of faith that you and your colleagues in this company would need to have in the model. You have to be sure that recurring runs of the model in future data lead to consistent, explainable results. Otherwise, you will lose credibility in the eyes of those who use this model to make decisions such as deciding whether or not to terminate employees. Given what I've said here, it should make sense that most machine learning algorithms are probably not suitable for this task, primarily due to the low explainability aspect. By the way, I want to mention that although this scenario sounds very dystopic, something similar to this scenario has actually happened in K-12 education, particularly with value-added modeling. If you click on the link in this footnote, it will take you to a Washington Post article which describes how value-added modeling fired a teacher and the ethical implications of value-added modeling. Value-added modeling, in particular, became so prevalent that the American Statistical Association felt the need to release a press release about it, which you can find here. I strongly encourage you to read these articles, as they are a good example of how careful one needs to be when using models in high-stakes situations. Here are some other examples that either I or someone who I know has had experience with regard to statistical modeling. When you're in situations such as these, or other high-stakes situations, here are some things you have to consider. Variable selection. In the case of variable selection, imagine running an employee retention model where you use age as a factor in your model. If people use your model to, say, intervene if your model indicates that someone is about to leave your company, how would that employee feel if they were told that age was one of the driving factors marking them as someone who could potentially leave the company? Or say, race. One has to be very careful about what data you use when doing statistical modeling. One also has to keep in mind the explainability of outputs of your model when you're in a high-stakes situation. It's also the reason why in some situations, one might prefer a simple regression model as opposed to a complicated machine learning algorithm. Thus, from an ethical perspective, it's a necessity that no matter what model you use, you need to know how tweaks, small or large, will affect your model output. Let's consider two more examples. Suppose you wanted to build a model to detect fraudulent activity. You have about 150 million transactions, and only about 0.1% of these transactions are actually fraudulent. Remember, every single model is a function which requires inputs. If you throw all this data into most models to detect fraudulent activity, it'll probably do a bad job of detecting fraud. Why? Because most of your data is not fraudulent data. As one last example, suppose you wanted to predict whether or not someone would commit a crime, and you throw all variables into your model, including age and race. How would you feel if law enforcement contacted you because you were likely to commit a crime because of your race according to a statistical model? All of these examples are meant to illustrate one point. More data isn't necessarily better for a model, despite what many people think, and the use of some data could be unethical and potentially illegal in some situations. For example, the GDPR requires companies to remove European citizens' data by request when it is being tracked online, whether the company's website is inside or outside of Europe. The maximum fine for non-compliance with the GDPR is $22 million or 4% of the value of the company, whichever is greater. That is to say, on top of general ethical concerns, one has to also take into account compliance with laws relating to collection and use of data. Here are some actual examples of consequences organizations have faced when investing a ton of money into AI. I strongly encourage you to read these articles. These are examples that still affect people to this day. So, now that we've talked a bit about ethical and legal implications of modeling, as well as explainability and complexity, where does math come in? Let's start by recalling the normal distribution. You would have learned this in the stats prerequisite course for DSci 2000. I don't need you to remember everything about the normal distribution except that it's a bell-shaped curve, the area under it is 1, and areas under it represent probabilities between 0 and 1. For example, this shaded area is the probability that you have a normally distributed quantity falling between -2 and -1. In reality, though, most quantities are not normally distributed. Here's something called the exponential distribution used in modeling lifetimes. What if we wanted to find this area here? With a TI-83 or 84, you could use the normal CDF function as you're usually taught in an intro stats class, or a normal distribution table. But neither of these options are available for the exponential distribution. So, how do you find that area under the exponential distribution? You need calculus. In particular, the computational techniques that you need to calculate that exponential distribution area are covered in Calc 1 and 2. This also shows why you need calculus in probability and statistics. Areas represent probabilities, and probabilities are needed to calculate things like means and variances in even practical settings. But that model is quite limited. Let's say you wanted to model profit and you need a model for revenues, costs, and how those revenues and costs interact with each other. Instead of a two-dimensional model using area, you would need a three-dimensional model incorporating volume. So you would need multivariable calculus, or Calc 3 in this situation. But reality is more complicated than just two variables. What if I wanted to be able to generalize to as many variables as I want? That's why you need linear algebra, which helps to provide this multidimensional framework. I hope by now it makes sense at a high level why data professionals need 3 semesters of calculus and linear algebra. One of the responses I get when I first presented this lecture is, Yang, I understand what you're saying, but I wouldn't be able to do it. That's a perfectly reasonable statement to make. It really shows how hard it is to master this material. From my perspective, I figure that if any of you are going to pursue a level 2 position, you should at least know why you need to learn all this math. That's the intent of this lecture. Now, let's take one last step forward. Note that we've only been talking about continuous functions so far, i.e. functions that you can draw without lifting up your pencil, like the normal distribution and exponential distribution. Functions that occur in reality aren't always continuous. Take stock prices, for example. These can be subject to leaps instantly when transactions occur. That's where real analysis comes in. It provides a framework beyond continuous functions, and it's usually taken beyond 3 semesters of calculus and a semester of linear algebra. That's all I have for this lecture. Please let me know if you have any questions.